Thank you very much for the invitation. It's an honor to give these talks. My first talk will be a colloquium style talk and will be about Syzygies of Algebraic Varieties. Syzygies, you say the following: the minimal greater 3 resolution E is unique up to isomorphism. Furthermore, the length of the minimal resolution is at most R+1. Recall that R+1 is the number of variables of this polynomial ring. The basic question is the following. So suppose that module is the ideal of some homogeneous variety, yeah? It's given by some homogeneous ideal, is of some projective variety X. Then one asks, basically, if we study the syzygy or study the resolution, what can one learn about the geometry of X from the syzygy or from the minimal resolution of E? So this is the kind of question one would like to know. A basic invariant is called the Casanova-Mumford regularity of E, which is weaker and hence a much more accessible invariant of the grading of the P dot. Instead of Betti number, one asks a slightly simpler question. The regularity of E is just defined to be maximum of all the j minus I, so the Bij of E is not equal to 0. A long-standing a conjecture by Eisenberg and Gordo say the following. Well, you say that, well, the regularity of Ix is bounded in a fairly simple manner by the degree of X and the codimension of X. So in this case, the conjecture actually predicts that regularity of Ix is equal to less than or equal to D minus E plus 1. What they did is somehow modify this real algebra in a way such that it becomes a projective variety inside a projective space in a fashion they can still control the complexity of the computation of the regularity. And in particular, what they show is that the conjecture itself is false if you're just assuming X is irreducible reduced and for dimension greater equal to 4, and more recent work of Hahn and Quark. Now, there are other progresses. So for instance, instead of the regularity of the ideal shape, one can look at the regularity of OX and their work of Jin-Young Park and Quark that saying that actually one can bound the regularity by D minus E. And in fact, they did a lot more. They classified the boundary example, maybe even the boundary example -1. Now, I mean, you can suppose you're giving a bunch of equations that defining the projective variety X inside PR. So you're given by a bunch of equations, yeah. And let's say they are defined by they define hypersurface of degree D1 up to Dm, and let order them such that D1 is greater equal to D2 up to Dm. Then the theorem that we proved is the following, that the regularity of Ix is bounded by D1 plus D2 up to DE, where E is a codimension minus E plus 1. And furthermore, the result is the boundary example where the regularity, the inequality of the regularity is an equality if and only if the X itself is a complete intersection of type D1 to DE. It just simply means that the natural map from S go to R by setting 1-to-1 is surjective. So basically saying that the module R is generated by a single generator given by the natural the element 1 in degree 0. And for each K positive to say L is satisfied NK, if it's satisfied N0, and together with the vanishing of the KP group, Q group, and in this range. And I mean, more concretely, you just simply say the following. Now, this is basically the classical theorem of Noether and Petri, saying that if C is a non-hyperelliptic curve, then KC satisfies N0. So that means the natural map from the polynomial ring to the abstract coordinate ring is surjective. And Petri is saying that the homogeneous ideal is generated by quadric. That means the N1 is just the sum of S minus 2. That just simply means that the curve is either trigonal. We see that trigonal is no good already, and or else it's a plane curve of degree 5. I leave it to you as an exercise to see that bigger than 2g plus k plus 1, then the L will satisfy nk. And this generalizes the classical result of. Now, the green conjecture just simply say the following. Saying that the canonical curve satisfies property nk if and only if the Clifford index is greater or equal to k. Roughly like 10 years ago or something like that, and Voisin proved that using K3 surface and Hilbert scheme of points of K3 to show that if C is a very general curve, then the conjecture is true. A few years ago, then Purdue, Vargas, and Papadima, and Reiku, and Weisman proved that using this representation theory and the tangent developable surface. So this is just simply the tangent union or the tangent line of a rational normal curve in PG. And it's known that such a thing is a degeneration of the K3 surface. And from that, basically, they give another proof of Voisin's theorem that's saying that the general canonical curve. Basically, you look at the dual of this resolution. What happened? Then the partial you resolve is this RC KC comma L, which is a direct sum of KC tensor LM. Yeah, and this guy here. Yeah. So this is linked it back to the canonical line bundle of the curve. And from that, it's not too surprising then. This should tell you a little bit about the gonality of the curve. And that turned out to be indeed the case. And so this is done by Lysershell, and I did it a few years, almost 10 years now, that saying that this gonality conjecture is true. And the proof, so the setup is something like this: LD but equal dA plus P. But if you want to just think about the case of L equal to dA, and RD is the number section, is the number section of this line bundle, and you form the, if B is any other divisor on X, you can form this called abstract module RBLD. And now we want to compute the Koszul homology of the syzygy of this thing when D is sufficiently large. And by regularity and things like that, one get a lot of vanishing theorem. And now, what happened? So the length of the resolution is RD, and RD basically is like big O of D to the n. So the length of the resolution is very long. So in things like NP property usually is only work for the first few terms, and it's basically linear with respect to D. And so you somehow ignoring a lot of information of what happened in between. And what this theorem is essentially saying that, yes, one can do this. And in fact, most of this group is non-zero in the possible non-zero range. And the basically is this see here. So it's here. This tells you that where it is the range where it's non-vanishing. So we proved that most of the terms are non-vanishing. But what we don't know was that whether this is asymptotic sharp. And Park was able to prove that 1 or 2 years ago, that in fact that this is the case. And he proved that in fact you get the vanishing in this range as we predicted. Of guess that just like the case of curves, you can see that sort of the Betti table. So if you fix, it's sort of like it's normally distributed. I mean, if you graph them, they sort of look like a bell curve. And one can ask whether this may be true in general or not, but again, knowledge about this kind of question is minimal.